Okay, ladies and gentlemen, let's continue with chapter 4. Chapter 4 is about transient heat conduction. Transient means how the temperature changes as a function of time, and the chapter consists out of 4 parts. The first one was the lumped system analysis, which we've already completed. Paragraph 4.2, which is transient heat conduction in large plane walls, long cylinders and spheres. That is what we're going to do today, and most probably we're also going to be busy with that. Not most probably, we are definitely going to be busy with that also with the next lecture. And then the part after that is transient heat conduction in semi-infinite solids, and then 4.4, transient heat conduction in multidimensional systems. And I hope that we will be able to finish it by the end of the week. Okay, so let's start with transient heat conduction in large plane walls, long cylinders and spheres. But before we do that, let's just go back to the lumped system approach. And just see again what the lumped system approach is all about and how this approach is going to differ with that of the lumped system approach. With the lumped system approach, we had a body, an arbitrary body. And this arbitrary body will be initially at a temperature Ti, and this is the environment temperature T infinite with the heat transfer coefficient H. So if we are interested in the temperature of this body, and let's suppose we take temperatures along this plane. There's X and there's Y, and we want to take temperatures at different discrete points. Okay. Our graph, if we plot the temperatures along this plane, the temperatures, let's suppose the body is at a higher temperature than that of the environment, so it is a hot body which is being cooled. So it means that at T equals 0, we will have the environment temperature, and then the temperatures in the body is going to look like that at T equals 0. Okay. So that temperature there would be equal to Ti, and this temperature would be equal to T infinite. So that is how the temperature measurements are going to look like. All of them here in the body is going to give us the same value, which is not realistic. We know that is not correct. Okay. So that is what the lumped system is all about. It's a very, very important assumption in the sense that we say that this resistance, the resistance of conduction divided by the resistance of convection, is the Biot number must be smaller than 0.1. So it means that it would give us a good answer if this resistance is 10 times smaller than that resistance. Okay, now at T equals 0, that is how the temperature is going to look like. 1 second later, if we take the measurements again, it's going to look like that. 10 seconds later, it's going to be like that. And at time equal infinity, then the temperature throughout the body is going to be the temperature of the environment. So it's not a realistic approach. In some cases, it's a good assumption. But in general, it's a very, very simplistic way of solving the temperature through a body. Now we are going to look at large plane walls, long cylinders, and spheres. Let's just define them. And they are defined in a graph like that, where this is the x-axis, and it sort of doesn't have a y-axis. It doesn't have a y-axis. So there's an x-axis, and this dimension in this direction should theoretically approach infinity. Okay. So it is a large plane wall. A large plane wall, and the emphasis is on large. It's large. The dimension, this thickness is going to be L. which means that the total thickness of the wall is equal to 2L. And this plane wall is going to be at an initial temperature Ti, at an initial temperature, when the environment temperature is going to be T infinite, just like previously with the lump system approach. And on the outside, there's a heat transfer coefficient H. Heat transfer coefficient H. Okay. And let's, it is not in the textbook, but let's put in here a length in the y direction, Ly. Ly. Okay. So somewhere in the small print, it says that the approach that we're going to use now is going to give good answers if this direction divided by L is typically larger or equal to 10. Larger or equal to 10, then this approach would give very good answers. Okay. So that is for the large plane wall. The long cylinder is very similar. There's the long cylinder. Theoretically, we would like it to be very, very long. It should approach infinity. And the coordinate system is an R coordinate system. And again, there's actually no y-axis. It's just an r-axis. And the radius is equal to r0, which means that the diameter is equal to 2 times r0. And this is called the long cylinder. A long cylinder. And then the third category of problem is the easiest of all of them, and that is the sphere with a radius also of r0, a diameter of 2 times r0, and this sphere do not have to be very large or very small. So where here it must be a large plane wall or a long cylinder, this can be any dimension. So those are the 3 types of categories of problems that we're going to solve now. Now, if we would typically look at the plane wall, we would typically look at the plane wall, and we would say that this plane wall, if we take temperature measurements on the inside, would be at the temperature Ti, while here the temperature is equal to T infinite. So in this case, we assume that the wall the large plane wall temperature is larger than that of the environment. So that is how the temperatures would look like at T equals 0. Okay, T equals 0. Now, at a small fraction of a time after T equals 0, if we would take temperature measurements through this plane wall, it's going to look like something like that. So that would be T1. Okay. And then the temperature distribution would start looking like that, T2, T3, and then after a while, this temperature in the center will not be equal to the initial temperature anymore. So we'll start doing something like that, T4, T5, and then at last, when T is equal to infinity, the temperature throughout the wall would be equal to that of the environment. So that is typically what is going to happen if we take temperature measurements through a large plane wall as a function of time. Okay. Now, in white, we've derived the different differential equations for continuity, linear momentum, angular momentum, and energy. But what I didn't do, and which should have happened last year, is in chapter 2, the energy equation was also derived in a little bit other form. So in future, we're going to use that energy equation. Okay, and the energy equation, in the textbook of Cengel and Ghajar looks like this. Partial d2t dx squared plus partial d2t dy squared plus partial d2t dz squared plus Egen divided by k is equal to 1 divided by alpha partial dt dt. Okay. What is Egen equal to? Egen is the heat being generated inside the control volume, which can be from electricity, a nuclear reaction, chemical reaction, anything like that. Alpha is equal to K divided by rho C, and that is called the thermal diffusivity. The thermal diffusivity. That is the energy equation. Okay. Now, to solve these problems, we are going to make certain assumptions. Okay. Quite a few of them. Okay. Now, the first assumption that we're going to make, assumption 1, is to say it is a one-dimensional problem. And that is why I've emphasized that we've got an x-axis, an r-axis, and an r-axis, but we do not have a y-axis. Okay. So this category of problem is about the heat transfer moving only in this direction. Okay. If this thing is very, very large, then what happens at the ends are negligible in terms of the total picture. Okay. So we are looking at a one-dimensional problem. If the assumption is one-dimensional and we look at the energy equation, then we can say that that term and that term is equal to 0 because of assumption 1. It's a one-dimensional problem in terms of the heat transfer. Okay. The second problem is, the second assumption is no internal heat generation. Okay. There's no nuclear reaction inside the body. There's no electrical resistance element, no chemical reaction, anything like that. So that term is also equal to 0. So the result is that we end up with partial d2t dx squared is equal to 1 divided by alpha dt dt. Okay. And we need to solve this problem with certain boundary conditions which are known. The first boundary condition, BC1, first boundary condition, says that the temperature gradient on the center line, the temperature gradient on the center line would be equal to 0, always. Okay, that's the first boundary condition. So dt, and I'm doing it now in terms of the large plane wall. Obviously, you can go and do it for the long cylinder and the sphere also. For the sphere, the equation is going to be look a little bit different, but it's the same principle. So partial dt is a function of x and t, dx is equal to partial dt, and now we want to know what happens when x is equal to 0. When x is equal to 0, dx, and we said that that should be equal to 0. The temperature gradient where x is equal to 0, the temperature gradient where x is equal to 0 is equal to 0. Okay, that is the first one. The second one, second boundary condition, says that at the wall, on the outside. Okay. This is now the wall of the large plane wall, or the surface. Then we can say on the surface, the conduction heat transfer on the surface must be equal to the convection heat transfer. So if we look at the heat transfer going through the surface, then the conduction heat transfer there should be equal to the convection heat transfer. Okay. So that gives us our second boundary condition. The second boundary condition says the conduction, which is equal to minus K partial dt, where x is equal to L. Where x is equal to L, dx is equal to the heat transfer coefficient multiplied by the temperature, where x is equal to L, minus T infinite. Okay. So that is our second boundary condition. But we need something else, and that is the initial condition. The initial condition. And the initial condition is that the temperature xt is equal to the temperature when T is equal to 0. The temperature when T is equal to 0 is equal to Ti. Okay, so what we have to do is, this is the equation, we have to solve it with two boundary conditions and an initial condition to get the answer. Okay. Unfortunately, it's not very simple to do that. And again, people a long time ago battled with this problem, and they actually managed to get a solution. And there are actually more than one solution. Obviously, some of them much more difficult, some of them much more easier. We are going to do the easy one, which is still difficult. Okay. Okay, now the easy one is to say, well, let's non-dimensionalize this problem. We are going to non-dimensionalize this problem. And we do that by defining, firstly, a capital X. And the capital X is equal to X divided by L. Okay. So X is any point here divided by L. So at this point, X is equal to 0, which means capital X is equal to 0. At this point here, X is equal to L, which means that X is equal to 1. So it means that X would always be between 0 and 1. Okay. So it is a dimensionless space variable that we've defined. It will always be between 0 and 1. So that is the first thing that we're going to define. Then we're also going to define a non-dimensionalized temperature, which is theta. The non-dimensionalized temperature, xt, is equal to the temperature minus T infinite divided by Ti minus T infinite. So that is the non-dimensionalized temperature. And again, that non-dimensionalized temperature will always be between 0 and 1. The next one is the Fourier number. The Fourier number, or the dimensionless time. And the Fourier number is equal to alpha t divided by L squared. It's the Fourier number, or dimensionless time. Dimensionless time. Okay, this one is dimensionless. Space, dimensionless space. That one is dimensionless temperature. That one is dimensionless time. And then the Biot number. which we've already defined, the Biot number, which is equal to H divided by KL, Biot number, and that gives us the dimensionless ratio of conduction divided by convection, the resistance of conduction divided by the resistance of convection. Okay. And the result is that this equation of us can now be written as, and we are not going to do the detailed mathematics, we can write that equation as equation looking like this. Now, why would we do that? We would do that because when we started this problem and we looked at the independent variables, the variables that would influence the temperature, then that would be X, it would be L, it would be T, K, alpha, H, Ti, and T infinite. So we had 8 independent variables that influences the temperature anywhere in that body. So the temperature is a function of all 8 the independent variables. After this process of making things in a non-dimensionalized form, the non-dimensionalized temperature is now a function of only 3 variables: X, the Biot number, and the Fourier number. Okay, if we go back to the lumped system approach, if we would go back to the lumped system approach and would use the same approach, then we can actually write that theta is equal to the non-dimensionalized temperature minus T infinite divided by the initial temperature minus T infinite is equal to E to the minus BT is equal to E minus H multiplied by the surface area multiplied by the time divided by rho, the volume, and Cp, and this can be written as E to the minus the Biot number multiplied by the Fourier number. Okay. So it's not relevant to what we're doing now. Okay. So don't go and use this result now for solving the temperature distribution in a sphere or something like this. That is just if we would use the same approach in the lumped system. For the lumped system, then we can get this equation. Okay. Now we are not going to do all the mathematics of the solution of this equation, but in this equation that we have now, which is still the energy equation that needs to be solved with lots of assumptions. It's a one-dimensional problem, no heat generation. And if we do that, there are 2 possibilities in terms of the solution process. The first one is to get the exact solution. Okay. And the second approach is to get an approximate. An approximate or a graphical and even a format sort of in a table format. Now in terms of the exact solution, that equation can be solved by doing a Laplace transform, by the separation of variables, and you can also do it numerically with the finite element method or the finite difference method. But we are going to use, or the method that is being used in the textbook is the method of the separation of variables. Separation of variables. Okay, now I'm going to spare you the mathematics. We're not going to go through every step of the mathematics, but in the solution, in the separation of variable solution, it's going to come out that there's an infinite number of roots. An infinite number of roots which can be determined by lambda n, tan lambda n is equal to the Biot number. And that is also called the characteristic equation or the eigenfunction. Characteristic equation or the eigenfunction. Okay. You've done that in mathematics. And the result of this is that theta is equal to an infinite series of n equal 1 to infinite of an e to the minus lambda n square multiplied by tau multiplied by cos of lambda n multiplied by x. Use the separation of variable methods, we get the eigenfunction. This eigenfunction have lots of solutions. It's not only one solution, it's an infinite series of solutions. Okay. Then at the same time, the non-dimensionalized temperature is equal to the sum of n equal to 1 to infinite of an e to the minus lambda n squared tau cos alpha n multiplied by x. And how do we solve this? What is this an now and stuff like that? Okay, alpha n, we need the solution of alpha n to put into there. Okay. And also for that term there. Okay. Tau, remember, is the non-dimensionalized temperature. The non-dimensionalized temperature. So if we want to know the temperature after 10 seconds, then it's easy to work out tau. So that is not a problem. So that one is easy to work out. But now we see an an here. An an. Okay. And the solution for an is not one solution. It's equal to 4 times sin alpha n divided by 2 times alpha n plus the sin of 2 times alpha n. So again, from the eigenfunctions, we are going to get alpha n. Okay. Alpha n. We're going to put it in there, and we can get the a values. Now let's look at an example which is given in your textbook, Cengel and Ghajar, figure 14.5. Figure 4.15. So if we look at figure 4.15, for a solution typically where the Biot number is equal to 5, what is the Biot number again? The Biot number is just the heat transfer coefficient of the air divided by the thermal conductivity of the body divided by the dimension of the body. So that's very simple to work out. So let's suppose the Butte number is equal to 5 and x is equal to 1. When will x be equal to 1? It would be on the surface. Okay, on the surface, and typically 0.2 seconds. Typically 0.2 seconds. If we would now go and solve n, alpha n, a n, and theta n. If n is equal to 1, okay, if n is equal to 1, then it's alpha ton of lambda is equal to the Butte number is 5. We need to get the solution of that, and the result would be that lambda is equal to 1.3138 and AN is equal to 1.2402. And if we put that into this equation, then we can solve theta where n is equal to 1. Okay, theta where n is equal to 1. And the result would be equal to 0.22321. And if we would repeat it now for n equal 2, then lambda would be equal to 4.0336. I'm not going to write down the value of AN now. And theta would be 0.00835. And the same for 3 and for 4. Okay. I'm just going to write down these values. So that would be equal to 0.00001. And in terms of 5 digits, that would all be equal to 0. And the exact values are shown there up in the slide. Figure 4.15, all the other values are given there for that solution. Okay, take a careful look at it. Take a careful critical look at it, and what do we see? We see that theta is then obviously equal to theta 1 plus theta 2 plus theta 3, etc. Okay. It's the sum of all the non-dimensionalized temperatures. The first one is equal to 0.22321 plus 0.00835 plus 0.00001 plus 0 in terms of 5 digits. Obviously, if you go and work it out with a computer, you will get maybe a 6th or a 7th or 8th digit. But what is important to see from the solution is that theta, fortunately, is becoming smaller and smaller very quickly. You see that? Okay, so if we look at theta, we can see it becomes very quickly very smaller. If we go and add it all together, it is equal to 0.23145. Okay. So in terms of the solution of the first term to the second term, it will only influence the second digit. So it decays very quickly. And in general, it has been found that if tau is larger than 0.2, if the non-dimensionalized time that you want, the solution for is larger than 0.2, the error would be less than 2%. Now this solution, ladies and gentlemen, is for the plane wall. Okay. For the cylinder, we're going to have a cylindrical coordinate system. The principle is going to be the same, but the answers are not going to be exactly the same. And the answers for that is given in table 4.1. So in table 4.1 is given the non-dimensionalized time for the wall, then for the cylinder, and for the sphere. Okay. So if you look there on the board, here are the solutions and the roots. And you will see they are not all the same in terms of the eigenfunctions. They differ. And very, very important, coming back to Colvin's question in terms of what we should remember, is that there's small print here, which is extremely important. Don't miss it. It gives you everything you need. It gives you the non-dimensionalized temperature. It gives you the Biot number. Take note, the Biot number is equal to H multiplied by L divided by K, or HR0 divided by K. Okay, so if it's a sphere, you work it out with R0. If it's a cylinder, also with R0. There's the Biot number, the Fourier number, and if you look very carefully, you're going to pick up something that many students pick up the first time in the test or exam. Okay, and that is that there are hidden a J0 and a J1. There's the J1. And there's the J0. Now what is that? Those are Bessel functions of the first kind. Bessel functions of the first kind. I'm sure you've done Bessel functions in mathematics. Okay. No. Question?
The bio number, I mean, the formula says H over KL, and there it says HL over K. I'm just on the board.
Yeah, okay. HL divided by K. Yes. Okay, thank you. Okay, so you see it is not necessary to remember the stuff, just look in the textbook. It's all there. Okay, so this is very important in terms of the solutions. Very important in terms of the solutions. And if you look at it very carefully, and again in terms of the Biot number, where we say that the Biot number is equal to H multiplied by L divided by K, ladies and gentlemen, very important. The L is not equal to the volume divided by the area as in the lump system approach. Okay, so this is only valid for the lump system approach, not for the Biot numbers calculated here. The Biot number calculated here is as defined there in the table. Okay. Now if we come back to the exact solution and the approximate solution, or the graphical or table solution. These days it's very easy to take quite a few terms into consideration in the solution of this. But if you have to go and work it out term by term, then it is very obvious to see that in some cases we can make very good approximations. Okay, we can get approximate solutions. And the approximate solutions would be if we take into consideration only one term, which is the first term. And as I've mentioned there, that would be when tau is larger than 0.2. If tau is larger than 0.2, then we will get very, very good answers if we take only into consideration the first term. Now, if we look at the first term, if we look at that equation there and we write it out for a plane wall, for a plane wall. Then theta, the non-dimensionalized temperature for a plane wall, is equal to temperature minus T infinite divided by Ti minus T infinite. That would then be equal to A1 e to the minus lambda 1 square multiplied by T multiplied by cos of lambda 1 multiplied by x divided by L. And that is equation 4.23 in your textbook. So that would then be the one-term approximation. There's a similar equation for the sphere, which will then be equations 424 and 425 in your textbook. I'm not going to write them down now. It's too long. It's going to take too much time. Okay. But what is very important to realize is that the constants A1 and lambda 1 are functions of the Biot number only. Only a function of the Biot number. Okay, and the writer of the textbook was very kind, or the writers of the textbook were very kind. In table 4.2, these values are given. Table 4.2. It gives us, maybe you can't see up there very well, because the print is very, very small, but it gives us the Biot number, firstly for a plane wall, and then it gives lambda 1 and A1 for the plane wall, then it gives it for a cylinder, and then for a sphere. For example, if the Biot number is equal to 2, then for a plane wall, lambda would be equal to 1.0769 and A1 would be equal to 1.1785. So if we look at this equation, equation 423, and we've got a problem where the Biot number is equal to 2, okay, we can say for a Biot number equal to 2, the non-dimensionalized temperature through a plane wall would be equal to 1.1785 e to the minus 1.0769 square multiplied by tau multiplied by cos of 1.0769 x divided by L. Do you agree? So the non-dimensionalized temperature, theta wall, is equal to A1, and A1 is equal to 1.1785 e to the minus lambda 1.0769 squared divided by tau, etc. So that would be the equation for it. But then there's another special case of problems, and that is the special case. The special case to get the values at the center. Get the values at the center. And if we are interested in the values at the center, then x would be equal to 0. And for that, we write it as the non-dimensionalized time, the 0 to indicate it is at the center, for a wall is equal to the temperature where at the center, temperature at the center, minus T infinite divided by Ti minus T infinite is equal to A1e to the minus lambda 1 square multiplied by tau. And that is equation 426. 427 is for the cylinder, and equation 428 is for the sphere. Now, if we take this solution, and this one, and we divide it with each other, then the theta at the wall divided by theta 0 at the wall, so that is at the center, would be equal always to cos lambda 1x divided by L. So it would be equal to a constant. What does that really mean? It means that if we have a problem where the center temperature drops with 20%, then all the other values would also drop by 20%. So that is what it means. Okay. If theta 0 drops with 20%, okay, it would mean that theta, all the other values would also drop by 20%. And this fact can then be used to also describe all the results in a graphical format, which is called the Heisler charts. The Heisler charts. And there are 3 of them for every one of the geometries. So in total there are 9 charts for the 3 geometries. Okay. And the charts look like this. The first one gives us theta 0. Take note, theta 0. And theta 0 is equal to the center temperature minus T infinite divided by Ti minus T infinite as a function of the non-dimensionalized time is equal to alpha T divided by L square as a function of 1 divided by the Biot number. So this would give the values at the center of the body. Okay, ladies and gentlemen, we've run out of time. We will continue with the next lecture. See you again tomorrow. Thank you very much.